Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover post-quantum TLS 1.3 with wolfSSL on the NXP FRDM-MCXN947 development board, presented by wolfSSL Senior Software Developer Anthony Hu and NXP Semiconductors Security Product Manager Stella Orr. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode. If you have questions, please use the Q&A box. After the presentation, Anthony and Stella will answer your questions. As always, our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with all the latest from wolfSSL, follow us on X, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to contact us via email at facts@wolfssl.com if you have any further questions. Next slide, please. Now let's take a quick look at today's agenda. We'll start with an introduction to wolfSSL, including a technology overview and a discussion of our key 5 competitive differentiators. Next, we'll hear from NXP Semiconductors with a company introduction. Stella will then highlight the features of the MCXN family, followed by Anthony, who will discuss the motivation for pursuing post-quantum cryptography and dive into the technical details of post-quantum TLS 1.3. Finally, we'll showcase a demo on the FRDM-MCXN947 and wrap up with a live Q&A session. And now I'd like to give a brief wolfSSL company overview. Next slide, please. Today, next slide again, sorry. Today, wolfSSL secures over 5 billion connections. We have more than 2,700 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers. This progress is, of course, supported by a strong partner network that we are very proud of. Next slide. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, a FIPS 140-3 certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfboot, Java wrappers and JSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Now I'd like to turn it over to Stella to introduce NXP and the FRDM MCXN947.
Thank you, Emma. Hello, everyone. I'm Stella Orr. I'm the product manager of the ecosystem team at NXP. So NXP is a semiconductor company providing processor for various applications, including automotive, industrial, and IoT. So our focus for today is for mass market application that use in industrial and IoT market. So next slide, please. So let me first start with the situation that we are facing right now. So in the past, for example, with the refrigerator, it's a very simple appliances at our home. But nowadays, the refrigerator is look quite different from in the past. So it is not just we just not using it for cooling and freezing any longer. We apart from cooling, freezing the food and drink, these smart refrigerator has camera, have sensor inside. It can tell you what products, what items are running now, and then add it to the items of your shopping list directly. And you can see from the image that some of the refrigerator, they equipped with a big screen that show you the shopping list. You can go online shopping and you can view and edit your shopping list from the screen and link it to your phone when you are in grocery shops. So the processor that needs to handle these complex tasks at the edge, which require higher processing horsepower, but we also need it to be power saving. And we want these appliances to connect to our personal device, for example, our phone. And because there's a lot of communication data sending between our personal device and these appliances. We also want security protection to protect the communication link between the device and the appliances. So we need data protection, we need communication link protection, and with these appliances operating at the edge, we also require AI at the edge that can help us to make decisions and give us some suggestions. Um, and also, we may also have other concerns like the quality, longevity, and also the supply resilience and cost and time to market. So these capacity factor leads us to this NXP to provide you guys a solutions called MCX portfolio. Next slide, please. So in NXP, we launched the MCX portfolio. Um, um, Starting from last year, it addressed all these complex requirements. So the MCX families provide uh, microcontroller solutions that are scalable from low-end applications to more advanced applications with the support of numerous technology enabled in the microcontrollers. Those technology includes security, edge AI, connectivity, functional safety, etc. And I will show more in my next slide. And then we provide not apart from the silicon, we also provide solutions that go beyond the silicon. We have the reference solutions for different applications, and we provide a strong ecosystem with different enablement available. So today, our focus is more on the security side, talk more about the security enablement that we have. And for production, we also support our customer with our trust provisioning solutions that allows you to securely program your part and provision your keys in your product. Next slide, please. So in this diagram, you can see that the MCX portfolio, it comes with six series in the MCX portfolio. And each series have its targeted feature set use case. For example, from let's start with the left-hand side, the M6C family. It is an entry-level MCX device with the lowest cost option, and it support USB and segment LCD with low power operation. And then going up a little bit, the MCXL, it is a eco-friendly microprocessor focusing on always-on battery power applications. And with the MCXA family, it can be used for intelligent edge applications. It offers the balance between uh, uh, the cost, performance, and also intelligent peripherals. And the next one is the MCXW series. It comes with some narrowband connectivity, and it provides you the capability for the network communication. And also it comes with some advanced security feature. And then the MCXE is for some applications that require advanced security and functional safety. And it has the extended temperature grade to support industrial application. And lastly, the M6N series, it is a multi-core microprocessor that provides you advanced performance, intelligent peripherals, and advanced security. So we will talk more about MCXN series for today. Next slide, please. So the M6N series, it is a dual-core processor running on the Cortex-M33 processor um, and 150 megahertz. Uh, and it comes with an Arm chip accelerator for signal processing and I/O interface management. And it also has the EIQ Neutron NPU for machine learning acceleration. It is available on some superset of the device. And it also provides a bunch of communication interfaces and analog peripherals. And for security, it comes with the Ashlock Secure Enclave. I will explain a little bit more about this. This is a very advanced features that we have on our processor, and it has its own dedicated resources for this processor. And it also provides you some crypto functions, also the secure boot functions on this device. And yeah, because all this security that we design in this chip, it allows us to get the CSIP level 3 and PSA level 3 certification. And next slide, please. Okay, so I will spend more time on this slide because it talks about uh, the security features that we have on this device. So M6N, it has the secure enclave design in the chip. It provides you the physical isolation because it has its own dedicated resources for keeping keys or sensitive information, and also the processing power. They are all have its own dedicated resources. Basically, we can use it for crypto service, including the TRNG and key generation, this kind of stuff. And for the secure key storage, we can also store it inside the secure enclave. And for key management over the air, we provide the Edgelock to go services, which we can link to the secure enclave of this device, exchange keys during the production. Because when when some of the product they go for production, they may want to protect their software IP. They may want to protect their unique keys, their device certificate. So with the Ashlock to go service that we have, it can enables you to connect to the M6N to provision your device securely. And also because MCXN can be used for some cloud applications that require the device to connect to the cloud. It can also generate the identity, the device certificates to prove its identity for the cloud onboarding. So we make use of the path to generate the unique identity for each device. And yes, for device and attestation, we also support the DICE function on this chip. And for the secure connection, it also support the TLS connection. And Anthony will talk more how we collaborate together with wolfSSL's PQC solution on securing the TLS communication. And this part, because it is a secure processor, it comes with the secure boot mode. That means in the ROM, it comes with the immutable ROM that allows you to protect your software IP. You can choose to sign your firmware, your software, and also you can encrypt it because on this chip it support the undefined memory encryption, and also if you prefer to store it in external flash, it can also support the on-the-fly memory encryption for the external flash. And um, uh, and also this chip, if you are working on some time-sensitive applications, you may want to have some encryption accelerator. So in this chip, it has the Ashlock accelerator that can help you with speeding up the public key cryptographic functions. And for the device and software integrity and confidentiality, we have the immutable boot ROM that I mentioned earlier. And on some of our M6N device, we support the dual boot mode. So the dual boot mode means that we support the traditional way with the ECDSA for signing. And because of the pros quantum crypto requirements on some of the application, we also add the ML-DSA uh, as add the ML-DSA in our secure bootloader to also support the post-quantum crypto. So the hybrid mode means that we can support both the ECDSA and the ML-DSA for boot up. And uh, and as I mentioned earlier, we support the Azure to Go service that help you to inject or program your credential keys and software, even though you work with a contract manufacturer, which usually in an untrusted environment. And with the PFR, the protected flash region, we use it to store the secure boot configuration, dice configuration, and your keys. And for some applications that may need tamper detection, for example, for some payment applications or some maybe network machine, they may need some tamper detection. It can also support, this chip can also support the security monitoring sensor. And on the right-hand side, if your application that requires to comply with some security regulations like the U.S. Trustmark or Cyber Resistance Act, uh, this product can fulfill the requirements on the right-hand side that can help you with those regulations. Next slide, please. Okay, so I talked about the left-hand side, all the security stuff that we have on the M6N. Um, so one thing I want to mention, the secure enclave is different from the trust zone. So trust zone is basically provides you the logical isolation between the secure world and non-secure world, and it is using the same core doing the logical isolation. So it is quite different from the physical isolations that we have on the secure enclave. We have a dedicated core that handling all the security processing and also the memory. So the difference between the trust zone and secure enclave is that the secure enclave provides you an extra layer, more robust physical isolation. So in NXP, we provide both solutions for you so that based on your use case, you can use the secure enclave and also enable the trust zone based on your applications. And in the middle of the slide, in the middle of the image, you can see that there's a Edge to Go that I mentioned earlier. It is our cloud service, cloud provisioning service that your device can use this service to inject your secret keys, inject all your secrets to the processor securely. And when the product is deployed in the field, you can also connect your product to the Edge to Go for key management or any lifecycle management. And on the right-hand side, this MCXN processor, it is already certified with the CSIP certification and also PSA level 3. And for industrial product, if you require the 62443 certification, we also have a application notes that you can find from nxp.com that can show you the mapping of the requirements, how we can help you to make use of the MCXN to fulfill the requirements for the 62443. And next slide, please. So, today in our demo, we will make use of the Freedom Board that NXP provide. So this Freedom Board is a very low-cost, scalable hardware platform and also supported by our unified MCU Special developer experience tool suite. And it provides you a consistent open source friendly environment. Um, and in the middle of the screen, you can see on top of the Freedom Board, if you work on some specific application, you may need to have some expansion boards that connect to the Freedom Board. You can find many different options from nxp.com about the expansion boards. And with the Freedom Board and expansion boards, it allows you to create a solution for your proof of concept at very low cost and also in a very simple way. And as you can see from this slide, NXP provide different technologies that include in the MCXN family. And these technology are supported by our MCU Special SDK. And also you can find some example code on GitHub and our application code hub. Next slide, please. Okay, so here I provide some links for you if you are interested in the Freedom Board and expansion boards. And today, Anthony is going to show you a demo for the TLS, which is already posted on our application code hub. So you can go there and check it out. And next slide, please. So this is going to show you how the application cookup looks like. So you can find the link on the top of the screen, top right of the screen. And these are some examples that we work together with wolfSSL to provide you some example code running on some of our device. Actually, mostly running on the same device, MCXN. With that, I hand it over to Anthony. Thank you.
Thank you, Stella.
Mhm.
I'm gonna go next slide. Luckily, I'm controlling, I'm driving this presentation, so I won't be saying next slide. Okay, so let's get into the motivation for going to post-quantum cryptography. Most people think it is a cryptographically relevant quantum computer. Um, so when are we going to get one? And who's going to have it? And who's going to invent it? And who's going to make it? And in reality, this is not actually relevant. Um, we don't need a cryptographically relevant quantum computer to need post-quantum cryptography. And there's some good reasons to say this. First of all, it's compliance. The most important part is compliance, right? NIST, NSA, all these European standards organizations, X9, including like the BSH, ETSI. X9 is a banking standards group, and all of these industry standards groups are writing up standards that basically tell you that you need to move to post-quantum cryptography, right? So it's not that a quantum computer is coming. It's that you need to follow the standards and guidance that these organizations are giving to you. Now they're giving these shall we say, this guidance because they know that a cryptographically relevant quantum computer is coming. So don't worry about the quantum computing. Worry about the people that give you the guidance and and worry about what they're thinking. Okay. Um, I put customer requirements at the bottom. That's kind of, it actually is part and parcel with what I'm saying there. Your customers are going to be listening to these standards organizations. So it's a great reason to follow them. So what are these organizations worried about? Well, they're worried about harvest now, decrypt later, which basically means that, there are these very rich criminal organizations and adversarial nation states that are basically vacuuming up your ciphertext that you're sending out on the internet and storing it so that later, when they do have a quantum computer, they'll be able to crack it because this quantum computer is basically able to break all of the cryptography that we normally use today. When I say normal, I'm talking about ECC, I'm talking about RSA and Diffie-Hellman. All of those are in the presence of a cryptographically relevant quantum computer. Those are now broken. Now, of course, we don't have one today, but how long do your secrets need to stay secret? Um, well, if it's more than 30 years, then you have a problem because we're most likely going to have a quantum computer within 30 years. So that's the harvest now, decrypt later threat model. The other threat model is, and that's basically a threat model for against confidentiality. The other threat model is against authentication, which is called deploy now and forge later. And what that model kind of says is like, okay, we're going to put our certificates out there. We're going to put our bootloaders out there, and they're going to be able to do proper authentication. Well, if you deploy now and you've deployed this stuff in, let's say, places that are hard to reach or inhospitable, there's a chance that you're gonna forget about these things, or you're not gonna bother, or it's gonna be too expensive to update. Great examples are space, right? If you're launching a satellite, you might lose track of it, and it might come back to bite you in the future because it was just too inhospitable to update uh, your your um, your firmware. Okay, so let's get into technical details now. There are a couple of gotchas out there. Um, One of them is that TLS 1.2 and DTLS 1.2 will not be getting these post-quantum algorithms. So our demo today is not going to be on DTLS 1.2 or TLS 1.2 for that matter. Our demo is going to be running on TLS 1.3. So why is that important? Well, it's important because a lot of people are still using TLS 1.2, and they, they a lot of people forget that, these algorithms won't be coming to TLS 1.2 because um, the thing is that these algorithms are like authentication algorithms, and the newer algorithms are authentication algorithms as well as key exchange algorithms. And they're not, and in TLS 1.2, the cipher suite defines those. In TLS 1.3, they're defined in the SIG-ALGs and the new groups and the groups extensions as code points. So what's going to happen moving forward at the IETF is that only the SIG-ALG and group code points are going to be defined for post-quantum algorithms. No new TLS 1.2 cipher suites will be defined. So at the very least, if you want to do something today, right now, the best idea is to move to either TLS 1.3 or DTLS 1.3. Um, so let's talk about wolfCrypt and the post-quantum implementations that are in there. Currently, we've already implemented LMS, XMSS, ML-KEM, which is formerly known as Kyber, and ML-DSA. Um, all of these algorithms are recommended by both NIST and the NSA's CNSA 2.0 guidance. Um, So we're not going to be doing a demo on LMS and XMS today. They're both stateful hash-based signature schemes. They're both they both have very nice public key sizes, very fast verification, but have large signatures. They're very appropriate for Wolf boot because what Wolf boot is, it's a bootloader basically, and it only does verification in terms of oh well no sorry the internal tooling does keygen and signing, but in in the field on devices it would be doing verification only, and it's very these algorithms are very good for verification. Now, one thing to keep in mind about these algorithms is that their performance is fine, and we'll get into benchmarking numbers later. You'll see that performance won't be an issue. But what is an issue is the artifact sizes. The artifact sizes are very, very large, right? We're talking kilobytes here. So if you're looking at the highest level of security, what's going over the wire? We're looking at ML-KEM as the key exchange mechanism here. And so what's going over the wire first is the public key, which is the encapsulation key. That's 1,568 bytes going right in the handshake, going back and forth, right? So the encapsulation key gets sent over, and then the ciphertext gets sent over, and then that's going to be decapsulated later. So that's approximately 3,000, more than 3,000 bytes going over the wire both ways. That's also memory that has to get allocated and be manipulated within on both sides. So you're going to have higher RAM requirements as well, memory requirements, sorry. With ML-DSA, the story is it's even a bit bigger, right? When you do a TLS connection, generally speaking, you're sending over at least one certificate, maybe two. Each certificate will have one public key and at least one signature, right? So that means this going over the wire at the highest level of security, which is ML-DSA 87, you're looking at, what is that, 2.5 kilobytes in the public key, and then another 5 kilobytes approximately. So that's just a certificate. Now, when you have within the TLS connection, you'll have also a certificate verify message, which actually has another signature in it. So that's another 5 kilobytes going, right? So that's about 12 kilobytes just in the handshake alone. just for doing authentication. You can see compared to ECC, this is a very, very large jump in data. So that's data going over the wire, and that's memory usage going up. Now, if you're just a normal web application, none of this really matters, right? Because you probably have gobs of RAM, gigabytes of RAM, and you have like really fast Ethernet or Wi-Fi. So this doesn't really matter. But in the embedded world, you can have use cases where, your transmission mediums are really slow. And, at 12 kilobytes, you just might feel that during the handshake. Okay, so let's look at TLS. So within TLS, we have our code points, and I'm just gonna do that. And we have, we support ML-KEM at levels 512, 768, and 1024. But we also do something which is really interesting, which is hybridizing with ECC. And so what we're looking at is um, hybridizing SecP256 ECC with 512 with ML-KEM 512, SecP 384 with ML-KEM 768, and SecP 521 with ML-KEM 1024. But for our European friends who seem to like X25519 and X448, we also hybridize with those. Um, for ML-DSA, we support ML-DSA 44, 65, and 87. Notably, we haven't hybridized those yet, but we do hybridize them in a special way, which is kind of outside the scope of this presentation. But we hybridize them with Chimera certificates. There are special certificates where the post-quantum side is added in as optional extensions. And if you have further questions about that, you can ask me during the Q&A. Let's get into the demo. Just to briefly, let you understand what's going on. Our firmware has a TLS server, and there's a there's a slight mistake on this slide. The server certificate and the server private key should be with the FRDM-MCXN947, and the root certificate is actually on the Linux PC side. And they're just going to be talking over TLS using post-quantum TLS 1.3. Yeah. It's notable for this demo that it's available already online. You can download these demos from our GitHub repo as well as NXP's app code hub. It's the same either way. The NXP's app code hub is just mirroring wolfSSL's GitHub repo, so it's you'll get the same thing no matter where you go. Okay, so on the FRDM side, the application is really interesting. What we do first is um, we run our benchmarks first. And then after the benchmark, and I'm going to go through this really fast because we're going to talk about the benchmarking numbers later. So don't worry, I'm just passing through this really quickly. The pink data here is the benchmarking output. And then after the benchmarks are done, we go into the TLS server application. And what this application is doing is basically doing a handshake and then, or sorry, it checks to see if we have the certificate and private key in NVRAM. If it's not in NVRAM, then we're going to use a default one that is built into the firmware. This default one is already in the firmware. So what's happening is that if it's not in the firmware yet, we're kind of going into an app. We're going to run this TLS server, which is going to wait for a client to provision it over Ethernet. And so what's happening here is we can see that there's a waiting for connection. The client side connects up, does the TLS handshake. You can see client connected successfully, and then they send over I can't remember if it was the public key that comes or the certificate. I think the certificate comes first, and then the private key comes later. So you can see receiving packets of 256 bytes all the way until the certificate comes, and um, then we see that we get 256 byte packets of the private key, and then now it shuts down. Now that it's provisioned, it shuts down. Okay, so on the Linux side, all we're really doing is building wolfSSL here. Um, and then we do what is this? Right. Then we build the client TLS 13 transfer.c application, and we send over the ML-DSA certificates. Um, this is worthy of note in that when you look at the data being sent, you can see that these are fairly large certificates, as I was mentioning. So this kind of highlights to you, how large these artifacts are, which is very, very important to consider as you're, especially in the embedded world where resources are at a premium. Okay, so really quickly, I just want to go into a bit about, some of the changes we made. We had to include the certificate in the firmware, so we compiled in the PEM as like a chart, as like a character, sorry, as a string. We had to add in, macros to specifically enable these algorithms. And that's basically because these are not standardized algorithms in TLS yet. So we have chosen to not enable them by default quite yet. Um, in the source code, we had to, so this is, this application is all available in the GitHub repos that I had mentioned before, but this was based on another application. And so I'm just going over the additions that were made specifically to make this quantum safe demo. And so we added the running of the benchmarks. So that's there. Um, the checking of the artifacts, whether they're in flash memory or not, we didn't actually do that. That was just sort of a kind of like a concept. This is kind of a concept idea. And so, we basically had these functions where we didn't implement them, but we just sort of assumed that they're just stub functions. And the reason why is because checking NVRAM is basically outside of the scope of this of this presentation. We're mainly focusing on TLS. And so yeah, the main code, this is really all the main code that had to change in the application to enable PQC. And that was, setting the certificate and the private key, the server certificate and the private key, and then as well as setting the key share to be used, which was P256 hybridized with ML-KEM 512. And so it's really important to understand where the post-quantum security comes in. So ML-DSA at 44 thwarts Shor's algorithm for authentication. For key establishment, we used ML-KEM at the 512 security level, and that was thwarting Shor's algorithm again. We're using symmetric encryption at AES 128, which, there's some debate as to whether that's strong enough. It depends on, who you listen to, but generally speaking, you're going to be fine. If you want to if you want to comply with even CNSA 1.0, you should actually be using AES 256, but it's fine. Okay. Oh, and a bonus is that since we were using ECC P256, we're actually also FIPS 140-3 compliant. Okay, so let's look at these benchmarking numbers. As I alluded to first, performance is not going to be an issue. When you look at these numbers, when people talk about post-quantum cryptography, a lot of people are scared that the performance is not going to be very good. And what we're seeing here is that performance is great. When you look at it, we can do 40. If you look at the security level of ECC at SecP 256R1, it's equivalent basically to ML-KEM 512. So these two algorithms, ML-KEM at 512 is basically at the same security level. Now, when you look at it, ECC's got, 4 ops per second, and then for keygen and 2 ops per second. We're looking at like 40, 66, and 50, right? So we're going to get a lot better performance, right? We're actually getting a lot better performance out of ML-KEM 512. Um, and as you go up the security levels, we're getting a little slower, but yeah, you're paying for higher security with time. Um, and the same story holds for ML-DSA, right? So if you look at let's not even worry about RSA because RSA has you know it's not it actually RSA is doing pretty good here. When we look at ECC, we're looking at, some fairly slow operation, relatively speaking, slow times because SecP 256 is at the same security level as ML-DSA. Now, during a TLS connection, we're not doing keygen. That's generally done offline, but we do a sign and a verify. And so when you look at it, you're getting two operations per second and 1 operations per second at sign verify, but we can get like 12 and 4. So, the performance is on par, if not just a little bit better. So performance again is not an issue. If you remember previously, we were looking at artifact sizes, and that is where you're going to see a big difference. All right, and that concludes our presentation. Again, if you wanted to try yourself, go right ahead and try go right ahead and download this and build it, and you can find all of this stuff on GitHub. Emma, I'm going to throw it back to you now for the Q&A part of this presentation.
Wonderful. Well, thank you, Anthony and Stella, for both of your presentations. If you have your hand raised, please just submit your question to the Q&A box and we'll get to it. Okay, to kick off the questions, do you support trusted firmware M on the MCXN? And what about support for MCU boot and Zephyr?
I can take that one. This is David Garski. So we have support in wolfboot, our own secure bootloader for the MCX-A and W. The MCX-N is a work in progress. If you're interested, just email us and we can accelerate that work. We also have wolfboot support for Zephyr, but MCU boot is an NXP part, or NXP product, and I don't know the status of that for the N. Maybe
Yeah.
Stella does.
So in our MCUX Special SDK, you can find some example that can support the TFN and also the MCU boot and Zephyr. And yeah, as David mentioned, we work closely to support you also the Zephyr and also the wolf boot.
Great. What are the difference between the security features of the MCXN and the MCXW family? Does wolfSSL post-quantum TLS 1.3 run on both families or MCXN only?
I can answer the first part of the question. So the difference between MCXN and MCXW. So MCXN, it run faster. It run at 150 megahertz, and the MCXW, it run lower, like 96 megahertz. And on the M6N, some of the device is support the NPU for the machine learning acceleration, but it doesn't support in the M6W. And M6W is majorly for the connectivity applications. So the M6W, it support multi-protocol connectivity, include Bluetooth, Thread, Zigbee, Matter, um, and yeah, and Wi-Fi. So the major difference is, I mean, in terms of the peripheral, is the connectivity. MCXW has all these connectivity peripheral. In terms of the security, they are quite similar. Yeah. So for the second part of the question, can it run post-quantum crypto, post-quantum TLS on both family? Maybe the questions to Anthony.
Yeah, so this is Anthony. wolfSSL basically runs on just about anything. We can build on just about any and every NXP part. So if it's a microcontroller, then for sure we build. For example, this example was built on with Zephyr, but we can go bare metal and we can go just about anywhere you need to in terms of the operating environment. So the answer is yes, it will run on the W series as well.
Wonderful. Is the ML-DSA in the bootloader implemented in software or hardware?
Stella, I
Um,
believe that means, yep.
yeah,
It-
I can. Yeah, I can talk a little bit, and then maybe Anthony and David, you can chime in. So yeah, I mentioned about some of the M6N products, it support the post-quantum crypto on the bootloader. So in that case, it is implemented in hardware. But we also work with wolfSSL on also providing the wolfboot that come with the post-quantum um, algorithm support. So maybe David or Anthony, you want to chime in and provide some more information for that?
in our bootloader in wolfboot, we support our ML-DSA and wolfCrypt, which supports just the software implementations. We have a pure C, and then we also have an assembly optimized version for Cortex-A, Cortex-M, and Intel. Um, I believe there is, well, I don't know about the status of the hardware ML-DSA. I just don't. But as of now, it's software. Meaning, I don't know if the chip has it or not. I can't remember.
Uh, yeah, it actually is coming up. It's not released yet,
Yeah.
but we are going to have one part from the M6 and that will support the hardware implementation. Yeah.
Wonderful. Do you believe harvest now, decrypt later attack is a valid concern for IoT deployments?
This is Anthony again, and I believe the concern is real. Um, you know, what's it, it's not really the concept of IoT that applies or doesn't apply. It applies to the data that's going over the the wire. So there could be personal data, location data, right? Like it's very let me give you a good example. Location-based data can go over IoT devices, and that can be sensitive. Where you are or where you were at some point, um, and where you were located at any given time might be a sensitive issue, even years down the road. And I don't want to kind of go into a spy versus spy kind of, narrative, but any personal data that's going over the wire is relatively it is vulnerable to this kind of attack.
Perfect. Is wolfSSL working on anything associated with hybrid certificates or composite certificates?
Why, yes. This is one of my favorite topics. So we're working with the X9 standards organizations under X9.146, and uh, there they are standardizing. They're trying to work with standardizing what are now called Chimera certificates. These are certificates with what are they called? With the public key and signature, sorry, alternative public key and an alternative signature in the X509 extensions. These are actually already standardized under the X509 standard, the 2019 edition of the X509 standards, that are maintained by the ITU-T. Um, Now, what X9 is also doing is they're adding TLS handshake extensions to negotiate the use of the um, the use of the alternative public key and signature within the certificate verify message. If you want more details on that, we've got webinars. You can email me at facts@wolfSSL.com and we can arrange a meeting and I can tell you all about it.
Awesome. Do you believe there is an urgency to use PQC algorithms for authentication in a TLS handshake? Eric Rescorla argues to focus on KEM usage.
Right. So there's, like I said earlier, there's two threat models, right? One is the harvest not decrypt later. I think we should take that very seriously. But I also think we need to take authentication seriously. Um, and I respect Eric Rescorla's opinions very, very much. He's been in the community for a very long time. Um, but I think he might be focused more on web applications and the wider kind of IT space. We're looking here at like bootloaders, right? So, do you need your device to be resilient against your bootloader to be resilient against authentication attacks? And if you're talking about things like cars that are in the field for, 20, 30 years, if you're in a really good climate, if you're in the tropics, you might be, or not the tropics, the Caribbean. I've seen cars that are still being driven from 50 or 60 years ago, right? So you have long-lived you're going to have long-lived devices out there. And if you're going to deploy and forget about them, then you should probably be very careful what you deploy. Thanks for that question. It was interesting.
Is the larger flash and RAM requirements for PQC keys a problem for the MCXN947 board when it has so much flash and RAM due to the AI use case?
It depends, right? So what we showed in this demo was a very rudimentary system, right? But one thing that wolfSSL prides herself on is the agility aspect of our code. When you build wolfSSL, we're very conscious of the embedded use case. And what that use case means, what that means is that we need the agility to make trade-offs, right? So code size, and we can trade off code size and RAM usage for speed with a high amount of agility. Now, is it enough such that you can, still have AI applications? Well, I'm sure there's trade-offs that can be made in the AI code as well. So we haven't gone far enough to explore having the AI applications work with our post-quantum algorithms, but I'm guessing it wouldn't be too big of an issue.
Perfect. Okay. For the ML-KEM implementation in wolfSSL and wolfCrypt, did you optimize the code for the MCXN947 board?
Okay. Actually, we just used what was default, which is typically optimized for speed. So if you look in our ML-KEM and ML-DSA source file, you can see that there are macros defined there for optimizations. And those are where the trade-offs come in. You can have a look there. Thanks for that question.
Wonderful. We're going to kind of rapid fire some questions here so we can stay within our time cutoff. But how is MCU boot going to coexist with Wolf boot?
They don't. They're both secure bootloaders and they're separate products used separately.
Perfect. Um, MCXN seems a little too slow for our application. Do you have any timeline for M7 based like RT 1170?
Yeah, so I can take that. So for the moment, for MCU, the RT1170 is our the fastest processor that come with the Cortex-M7. Um, yeah, so we always look into having explaining our product line, but I don't have the timeline to share. But just to say that the RT 1170 is the highest fastest processor that can support the M7.
Wonderful. Does Wolfboot support the NXP S32K3 family series?
Not out of the box, but it would be a very easy effort. It's a Cortex-M7, and we have customers using similar parts like that. It's just not on our roadmap. But if you're interested in getting it added, just email fax at wolfSSL.
Can the security provisioning tool from NXP be used with Wolfboot?
No.
No. Currently we don't. Yes, I think that is something we can think about, maybe with David to see some more integrations to make it more ease of use.
Is this to tie into the root of trust? Is that what that is? Like the
Um,
hardware-based authentication?
Yeah, so the secure provisioning tools is the tools that customer they can use it for sign the image. So with the Wolfboot, we may probably can think about integrate some integration with the signing inside the secure provisioning tools.
Yes. Yes, we
Hmm.
should definitely do that. Mhm.
Yep.
Fabulous. And then I think our final question, how easy is it today to just pull the raw ML-KEM and ML-DSA functions out of wolfSSL and use them on a small Cortex M33 device like a hardware wallet?
So I guess I can take that one. It's fairly simple in the sense that I think the only real dependency it has is on what is it called? Shake. So we have a Shake 256 and a Shake 128 implementation in there. So it depends on that. I think it might depend on some of the math libraries as well. So you probably have to, pull out those things as well. I think the best idea is to just try a build of wolfSSL, and you can disable just about any and every algorithm in there if you need to, and see how small of a binary you get, and then start looking at the trade-offs within the ML-KEM and ML-DSA files to see if you can get it even smaller.
Perfect. Well, thank you, Anthony, Stella, and David, for hosting an informative webinar. Thank you to everyone for joining. You can keep up with our upcoming events, meet our team in person, read our blog posts, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions, please reach out to us at fax@wolfSSL.com. Thank you all.